Hello, everybody. I hope you're doing well and you are making progress on your Calculus 3. This is section 4.5. Where am I? Well, what you're seeing here is the background picture that I have chosen for today, and it is one of those saddles. It's not exactly a hyperbolic paraboloid, but it is similar. And you can see that I have graphed this and did a screenshot on Good Grapher, and I have two horizontal planes which are intersecting. You can see the hyperbola on the top red surface and the degenerate type of hyperbola, which becomes two lines, and that's the middle or the bottom horizontal surface where you can see the crossing, which is basically at the origin. All right. Well, hi everybody. Okay, so this is the kind of thing that you should be able to see. And again, I should tell you, when I was a student, this is something that we couldn't even imagine being able to hold in our hand and see the graphs. Okay, so I would strongly encourage you to take advantage of the technology available today. All right, so this is a lesson. This is a lesson video on section 4.5, which is chain rules. Now, this may be a surprise to you, because you learned the chain rule in Calculus 1, and you used it thousands of times, probably, right? Because I would say most of the functions that you deal with are compositions, F composed with G or G composed with F, and you would have to use that chain rule frequently. Well, it turns out, because we are now in multivariable calculus, we have a few different versions of the chain rule. So we will call this chain rules, okay, with a big S at the end. All right, so let's study the chain rules. How do we stop this? Okay. All right, here we go. Okay, section 4.5. And as I said, it's on chain rules. Is that okay? Yeah. I mean, I have to make sure that you understand there are several versions of this, right? How do I start every lesson in Calculus 3? Exactly. I start with a similar lesson in Calculus 1, because basically that's all we do in Calculus 3. We just add a dimension or two to Calculus 1. And of course, if you add, two dimensions, then Calculus 1 becomes Calculus 3. That's just two more than one. Anyway, the chain rule, how do you do the chain rule? Okay, so this is the background, right? So you know what a composition is, right? And again, through a sort of an unfortunate series of events in the history of mathematics, we have to read, in this particular case, from right to left, because somebody sort of messed up, in my mind, on the notation of functions, okay? You take x and place it into G, okay, and that's called, well, okay, so let's say you have this box called G, right? Because that's really what's happening in the functions, all right? And then what comes out is G of X, right? And then G of X is immediately placed into another box called F, okay? And so the second function that is operated on the outcome of G of X is F. And then what comes out is F of G of X, right? And even though you write F first, you actually do F second, all right? The composition of F of G is actually this big box. So you package these two machines into one box, and this is called F composed with G. Remember, you do G first, even though you read from left to right, F of G. And so that's the composition. And what happens here, oh, by the way, G is often called the inside function because that appears in inside. And F is called the outside function. This is the notation that you learned many years ago, probably, right? And think of this G, sometimes this G of U, G of X is called U, okay? Because because we talk about U substitution. And if you remember what U substitution is in integration, it's basically how to deal with the composition where you call the inside function U, okay? So, and that's one of the best things in integration, right? The U substitution. Again, you use them over and over and over again, just as the chain rule for differentiation, because many functions just happen to be compositions of one or two or three or more functions. Okay, so the inside function is often called U. And so this, unfortunately, is called f of U. And so U is the inside function, f is the outside function. The chain rule, as you know, is used to take the derivative of this composition y. And so y prime is f prime evaluated at the inside function times g prime of U. Okay, we also denote this as dy dx. Okay, because that's what you're looking for, right? Is equal to what? Well, the first part is actually dy, because y is basically f of du. So you take the derivative of y with respect to u, and then remember g prime is basically u prime, so it's du dx. And so if you write it this way, it looks almost like multiplication where the du's will cancel, right? Okay, so that's really what the chain rule is. Now, you may wonder why it's called the chain rule. Well, I'm glad you asked, because most people don't answer this question. Most books don't answer this question. Here's the great way to illustrate this, right? And I have, I really think this is an awesome way to think about this. All right, so if you have a, like a 5-speed or 10-speed or 21-speed bike, they come with, chains, right? And gears, all right? And your cars come with gears. You can go from first to shift, you shift from first to second. Most cars now have automatic shift. And, but, you still have gears. They're in a thing called gearbox. So you don't typically see these gears anymore, but every car has a gear. Students sometimes say, no, my car has no gears. I've never seen them. Yeah, of course you don't see them because they're in the bottom of your car. But anyway, so you have these gears, and what gears do is, shift your speed, because your car can't start on the high gear any more than you can start in the bicycle on high gear, especially if you're going, uphill. You start with lower gear, first gear, and then you go to second, and then third, maybe, and then you go to fourth, and then up to 21st if you have a 21-speed bicycle. All right, and so gears kind of work this way. And the way I'm describing this in this metaphor, the first one is x. That's the independent variable. All right, you apply g first. So the second gear is gx, which is called u, and then you plug in u into f, and then this is, of course, f of g of x, right? This whole system of gears is your composition of two functions, okay? And let's say, for the sake of example here, every time you turn this wheel once, like it could be like the pedals, and if you just turn this one time, because of the difference in radius, this would actually go 3 times. You see that? Because this is much smaller than this, right? So if you turn this once, if you just turn this circle one complete cycle, then this will go around 3 times, okay? Now here is the gear U, and here is this gear Y, all right? You turn this once, this goes around 3 times. Let's say the ratio between the second and the third is 1 to 2. Okay, so every time you turn U once, then Y goes around twice. Get the picture here? Okay, so ratio between this and this is 1 to 3. And then this to this is 1 to 2. Okay, so here is the question that you probably are aware that I'm about to ask you. What happens to Y if I turn this X once, right? So I'm going to take this and then make this rotate 1 time. That would turn this one 3 times, right? And remember, every time this one turns once, this one goes around twice. So if you go around here 3 times, how much is this going to go around the last one? Right? Yeah, 1, 2, 3, 4, 5, 6 times. Right? Why is it? Well, because here for 1, this will go around 3 times, and 3 to 6 is the ratio. What I just described is exactly the chain rule. Okay, you see, you multiply these, and that's because like this. So what I'm saying is like this was 3. Remember dy du, that's how many times y turns with respect to u, that's 3. And du dx is how many times u turns for each turn of x. That's the rate, remember this is the rate or the instantaneous rate of increase, right? And so this will be 2. You multiply them. Why? Well, it's pretty obvious if you think of the gear system. You multiply because of these chains. And guess what? This is why it's called the chain rule. Okay, these are chained together to form a composition of 2 functions. Okay, so that's exactly what's going on. All right, now done with calculus 1. Let's go to calculus 3 now. Remember, if z is f of xy, we had a thing called the total differential. df, sometimes called dz, it's the same thing. It's the partial of f with respect to x times dx, and then plus partial of y with partial of f with respect to y times dy. Okay, and again, the picture was, you had a function like this, and oops, I don't want that. So that's okay. So if you have a function like this, f, right, and then we are trying to find the linearization, or we were going to, so what I mean, because differential is basically a linear approximation, right? So this is the tangent plane, and on the tangent plane are these vectors. One is fx and one is fy, and the tangent plane, of course, contains both fx and fy, and so you can see, I mean, this is just an illustration, but you can see that when you add these 2 things, okay, so this is dy and this is dx, and that's going to give you the total difference between the value of the function at this point and the value of the function nearby, and that is what the linear approximation is. Okay, so here are the different versions of the chain rule, the chain rules now. Okay, so let me give you a couple of cases. Case number 1, right? Assume that z is f of xy. Okay, so you have 2 variables, and x is a function of t. Let me just write this as xt. Okay, y is also a function of t. So we have one parameter t giving you both x and y. Right, so remember, this is important. This is the first case where both x and y are of the same parameter, namely t. So each is a function of the same variable, t. All right. In this case, the picture is this. Z is f, which has x and y, right? But x and y both have the same component or the same parameter, t. Okay. I personally like to have a t together, but I will keep them separate like the book does. All right. In this case, right, we have what is the thing that we're trying to find? If you're trying to imitate or emulate the chain rule, what we are looking for is dz dt, right? How much does z change instantaneously with respect to t? That's the question, because this is the composition, right? We have this part and we have this part. So the composition is that z is basically a function of t, okay? And so that is the partial of z with respect to x times dx dt. Plus, remember, because of this addition, it is defined in the total differential. Maybe I should write down that word here, total differential. I know I'm talking very theoretically. Don't worry, I will do examples. And the examples and the problems in this section really aren't that hard. I think you will get this very quickly. So do not be afraid. Do not fret. All right, so partial of z with respect to y, and then dy dx. And so that's, oh, sorry, this is t. Okay, of course it's t, because that's what you are differentiating with respect to eventually. All right, so that's not very difficult. And notice here, I want you to be very, very careful about what I wrote, okay? And I want you to be just as careful when you write. Every time you have a function that depends on more than one variable, like z, okay? I have the partial notation here, okay? These are partials. Of course, you can write them as zx or zy, but traditionally for chain rules, we use the partial notation, like the one I did. But see, x and y only have one variables. Okay, so I'm not going to write something like, don't write, partial of y with respect to t, because y is a function of one variable. There are no partials. All right, so do not write this. Do not write that if x only depends on one variable. Right, and that's why you see both the d and the partial notation here. Okay, so that's the first case. Sometimes the setting is different. Z could be still a function of x and f, function of x and y, but x may have two parameters. Y may also have the same two parameters. Okay, so we have a multivariable function of x and y, but x and y could themselves be multivariable functions. You see the difference? Okay, so each is a multivariable function of t and s. We have various things here. Basically, this is what's happening. F has x and y. X depends on s and t. Y also depend on s and t. So here we have two function or two chain rules. dz of the s is one thing you can look for, and then dz of the t. Now they are very similar, and you can quickly get the pattern here. This is partial of z with respect to x times partial of x with respect to s. Notice here, because x is multivariable, this is the partial, not the lowercase d anymore. Plus partial of z, partial with respect to y, times the partial of y with respect to s. T doesn't appear because we are not differentiating with respect to t. Now, similarly, the partial of z with respect to t is the partial of z with respect to x, partial x with respect to t, plus partial of z with respect to y, partial of y with respect to t. So maybe I should differentiate s and t, no pun intended. Okay, we differentiate with colors. Okay, so you can see that this is just s and this is just t, and the other parameters do not appear in these cases. All right, so most general, I mean, this is not the most general case, but you can make this general. Okay, what happens if f has x, y, and z? Okay, f is a function of three parameters or functions, and if these each are s and t, and maybe you have even more, and you can set this level, you can have let's say n variables, and at this level each of them could have like m variables, and then you'll have m different chain rules. Okay, so but I'm not going to make it that general because that's just we don't need that level of generality. All right, so here if you have this, it's very similar. Let's say z is this function f, or you can write this as a partial of f or partial of z with respect to s is equal to partial of z with respect to x, partial of x with respect to t, so s, and partial of z with respect to y, partial of y with respect to s, plus, and you remember you have, oh, sorry, I can't do that, do I, can I? Because z is already here. All right, so sorry about that. Let's call this w, so I can't use this here. All right, so all of these are w's. That's good, I caught that. All right, so a partial of w with respect to s is partial w with respect to x times the partial of x with respect to s, plus similar for y and similar for z. That's not z here. This is supposed to be a w, and this is z, and then dz ds. Okay. Now you can probably just go ahead and write this down, right? I mean, you may just want to write it down, make sure you understand it. The only difference here is every s will be replaced by t. Okay, so you can probably do this faster than I can. but you will remember, have three parts, right? Or three summands or three terms, just because you have three variables at this level. All right, so I think what I wrote, even while I was talking, is still correct. And so you'll see T everywhere here. All right, it's time for an example. Like I said, this is really not that difficult. All right, so I think you can get it fairly quickly. Let's go ahead and do this example. And in fact, maybe I will stop after I pose this question and let you figure this out. And we'll come back to it. By the way, there's also a convention here that you don't leave X and Y in your final answer. Okay, so write your find. So the question here is find the partial of F with respect, sorry. F actually depends on T only in this case. This is the first case scenario. So this is dF dt, not the partial, okay? And do not use X and Y in your answer, okay? That's sort of a standard procedure, not necessarily the case for every single problem, but that's typically the procedure. Okay, try to find this using the newly learned chain rules, okay? And then when you are done with it, I'll come back and work this together.